let's start with the first of the inter-process communication methods, that is the mailbox. So, a mailbox is a mechanism to exchange messages between processes. Data can be sent to a mailbox by one process and retrieved by another. So, by processes, what we mean is that, for example, if you have a verification environment in which the generator, driver, scoreboard, monitor, checker, assertion list, they all are there, and you want to share the data between all these. So, for example, you need to check that whether the data which is getting generated by the generator is that the same when the driver is driving into the dirt, or whether the driver which is or whether the dirt which is actually producing the output, is it exactly the same which was intended for the particular set of inputs. So in that case, you may require that from the generator end, the data which is being generated by the generator, that data is being pushed into some data holder, and that holder can actually produce the same data at the other end where the output is getting generated. So in this way, like for in a particular verification environment, you can have hooks at various ends, and each end can have the data pushed into or get out of or fetch data from a particular data holder, and can see whether the data is coherent or whether data is produced in a correct sequence or an order or so. So mailbox basically does the same. What it does is that it actually exchanges messages between different processes, and it can also be used as a FIFO. Like you can push data from the generator end into a FIFO, and that FIFO, the other end, will be connected to a driver or to the scoreboard or to the monitor, wherever you want. So and there's also no restriction on the data. So data can be any valid system Verilog data types, including class data types, strings, index, anything. Similarly, mailbox is a built-in class, so which provide additional functionalities through various methods. Like the first is you need to create a handle of that mailbox, and that can be created very easily by calling a function new. You can also place a message in the mailbox through function put. You can fetch the data or the mail or message from the mailbox through function get or peek. There's also a concept of blocking and non-blocking, which I will explain you in just a few moments. For the time now, just understand that there can be a non-blocking way of calling functions like try put and try peek. Uh, Other than that, you can have the size of the messages in the mailbox, and that can be calculated through num. So let us come back to what is a blocking call and a non-blocking call. So in case of a blocking call, what happens is that if one of the process is trying to put data into a mailbox, and if mailbox is not available at that time, so a blocking call will ensure that mailbox will allow the data from that process to push into it. In that sense, that even if the mailbox is being used by some other process and the mailbox is not available at that moment, this blocking call will wait for that process to end, and once the process is over, then this process will feed data into the mailbox. So that waiting is generally termed into a blocking call in a system Verilog. Now, in case of a non-blocking call, what happens that if the mailbox is not available to take in some new data, then what will happen that that function that call that try put or try get or try peek will check for the availability of the mailbox. If the mailbox is available, then it's well and fine, and the data will be pushed into or fetched out. If the mailbox is not available at that moment, then this function will not complete, and it will just move out of that function. So that's basically a non-blocking call, and there won't be an intrinsic weight in this call. So these are the two ways by which mailbox can be accessed, either through a blocking call or through a non-blocking call. Both are exactly very necessary. I'll try to explain you in the next slide how this blocking call and non-blocking call can be used. So let us take an example of this mailbox example. So in the initial begin, what we are trying to do, we are trying to create a new handle for the mailbox, and that is creation is named as my mailbox. Now, if the mailbox creation is successful, this will proceed. Otherwise, it will get out of the if block and will just go to the end of the program. So if the mailbox creation is successful, what it will do, that it will spawn three threads. Three threads will be spawned here. The first is put, second is get, and this hash 1000 is also a actually a separate thread. And this fork join any won't wait for completion of any thread. It will just spawn the threads and it will come back to the end of this if in block, and it will continue to go to hashed weight of hashed 1000. So what happens here, that the put packets will be a separate thread, a get packet will again be a separate thread, and hash 10,000 will also be a separate thread. So what happens in the put packet, that it at there is an iteration of for I equal to 0 to 10, and in each iteration the code waits for 10 cycle and put the value of I into the mailbox, and then it displays that done put in data in the mailbox, and then it completes the task. In the get packet, what it says, that it again plays an iteration of 0 to 10 and it tries to get the data. Now you can see that this is a blocking call. This put and get is a blocking call, in which the get will wait until and unless a put had happened, and once the put has happened, the get will get the data. You can see from the display that once a packet has been put at time 10, the get, even though there is no hash 10 in the get packet task, it still wait for the time scale of 10 nanosecond or 10 clock cycle, whatever it is, and only at that moment it will get packet 0. So in this way there's an intrinsic wait actually happening in the second task, second thread basically, which by which it waits for the 10 clock cycles to happen, and then only it can get a new data. Another approach can be a non-blocking way, in which what happens is that for the fork join, you put packet, then wait for hash 1000, and then get packet. Now what will happen, and then you do a join. Now what will happen in this case is that once the put packet is done, okay, it will wait for hash 1000 and then it will call the get packet. So what will in this case the put packet will ensure that all the 10 data is pushed into the mailbox. It wait for 1000 cycles and then a get packet will call. Now even if in the get packet, if you try to call try get, okay, since the mailbox has all the 10 data and the mailbox is available, it will try to give out all the 10 data, and there won't be any waiting call or any non-blocking call. You can try that out in your system and to see how the non-blocking and a blocking call differs from each other. You can also remove this fork join here. You can also remove this fork join and just call initial in between the initial begin block put packet. There will be one thread which will do 10 iteration, then wait for 1000 cycles, and then you call get packet. In this case as well, there won't be any waiting call, and a non-blocking can be easily reproduced. So that completes our mailbox example. Let's continue with the semaphores. So semaphore is also a good way of inter-process communication. In mailbox is basically a handle to for the threads to communicate with each other. So like a particular block of process want to share information or want to share data with some other block, that can use mailbox. Now if in a design, if in a verification environment, if a particular process want to use a common resources, for example, there's a global variable and that variable is being used by the generator as well, it is being used by the scoreboard as well and by the monitor as well. Now if they all try to use it at the same time, then there might be corruption of data and the verification environment and the verification target is not achieved correctly. So it may happen that at one particular time of instance, a generator can use that resource, then it will leave that resource, then the monitor can have it, monitor will use that resource, and then it will pass on to the scoreboard. So that kind of sequencing, or that kind of uh, non-mutexing basically is actually achieved through semaphores in system Verilog. So system Verilog, semaphores are used for common resources. Semaphore is used for lock or unlock of a common resources. If a resource is in unlock state, the resource can be used. If it is in the lock state, then it cannot be used. Actually, it is restricted for the other blocks to use that. So following methods in this are supported. One is the new. New basically will create a semaphore handle. Then get is you need to get a semaphore key, uh, and then there's the task put basically, which basically put the key count as equal to 0. Then there's a return semaphore keys. This put will return the whatever semaphore is. And try get is again a non-blocking way to get the semaphore. Try put is the blocking way to get the semaphore. Okay, so this is a program which explains the semaphore example in a much detailed way. So what happens is that in the semaphore, in the global scope, semaphore SEMbus is created and with a key 1. So in the initial begin, there are two agents, agent 0, comma 5, and agent 1, comma 20. So what happens now, that in the task automatic agent, now you can see there is a use of automatic in which by which this whole task will be relocated on fresh new space. This has been told in the first 5 to 10 slides in this presentation. So as you can see that task or function can also be called as an automatic task or functions. So getting back to it again. So what happens here, that the task automatic agent accepts string name and integer n weight. So what it does is that it goes to a loop of I equal to 0 to 4, and it tries to get the semaphore bus of key 1. So what it does, it got the lock of semaphore bus which is denoted by the semaphore key 1, and then it waits for some n wait cycle, like for 5 wait cycle in the first case of the agent. It waits for the 5 wait cycle, and then it displays, and then it puts that semaphore key back into unlocked resources, and then it again waits. So you can see the output is that at 0th time scale, the lock SEMbus is for agent 0. Then for 5, it releases the SEMbus for agent 0. For 5, it again locks the SEMbus for agent 1, and then again 25, it releases the SEMbus for agent 1. So for first 5 clock cycles, agent 0 has the control of the semaphore bus. For the next 5 to 25 cycles, agent 1 has the semaphore bus. So in this way, the design is continued till 145 clock cycle, and you can see that agent 0 and agent 1 are basically interacting with each other, and alternatively they are getting the control of the semaphore bus. So events basically are the third kind of interprocess communication after the mailbox and semaphore. Mailbox and semaphore were introduced in system Verilog. Events were also there in the Verilog, and this event is basically our static objects which can be triggered via this operator and can be read upon by an at operator. So mailbox and semaphore basically was used for communication between the interprocess communication. What the event does is that event gives you a controlling mechanism by which you can basically control two different processes. So in that way, events are very useful. So triggering event can be any named events which are triggered via the dash and the greater than symbol operator. The same as in Verilog. Triggering an event unblocks all processes currently waiting for that event. So suppose in the module test, you basically wait for a variable x. Okay, so event x and y are two variables, and you just wait for x. Now it in fork add and sub join any. In the fork function, you are calling two tasks, add or subtract. In add or subtract, you basically are waiting for x at x. So once this x is triggered, here, this will unblock this event. So at x is unblocked at this event, and then add will proceed. Now once add is proceed, this y is triggered, and this y is unblocking task sub. So basically in this particular example, you have actually spawned two different thread, add and subtract, but they are interdependent on each other because of the events. So the first initial begin block actually actually starts the task add, and once add is done, it starts the task sub. So even though the two threads were spawned at the same time, there is an inherent sequencing which is happening here. So similarly, this is a waiting event which is triggered via the event control operator at. Okay, so let's get on to an important concept of assertions in system Verilog. So assertion, what are the assertion types? So basically, there are two kind of assertions: immediate assertions and concurrent assertions. So immediate assertions are based on simulation event. For example, if there is a condition in which you are checking whether A is equal to B, and if it is true, then there would be an assertion which will be thrown. So basically, it is assertions are basically a mechanism by which you can actually check whether a particular event has happened correctly or not. This can also be useful in checkers, where you want to see whether a design has performed or has behaved in a normal way or not. So there can be the assertions can be obviously an immediate way, where at the immediate clock edge you see whether the various signals are behaving normally or not. So immediate assertions are basically used only with dynamic simulation tools and used without property keyword, and they are generally placed in a procedural block definition. Concurrent assertions are basically spread over some multiple clock cycles. For example, there is a write operation or a read operation which which happens in around like 10 cycles, and you generally generate an address, then generate a data, and then you wait for the response. And in the 10 clock cycle, a response should come. So if in the 10th clock cycle a response doesn't come, then that is a protocol violation here. If the specs tells you that is the behavior of the DUT, in such cases concurrent assertions are done. So what will happen, that at the first clock edge, this assertion will start seeing whether the write process is happening correctly or not. So at time t equal to 0, it will start. It will wait for the 10th clock cycle that a response has been received for that write or not. If the response will be received, then there will be no assertion which will be fired. If the response is not received, then an assertion will be fired that your DUT is not behaving correctly, and please check it. So these are called the concurrent assertions. So concurrent assertions are based on clock cycles. They are used with both formal and dynamic simulation tool, used with keyword property, and placed in procedural blocks, modules, interfaces, or program definitions. So this is a particular example of an assertion in which this is a time t, and always at POSH clock you check whether the state is equal to request. Now you are seeing whether request 1 or request 2 is high or not. If any of the request is high, you will assert, and if it is not, then you will flash an error that assertion is failed at time t equal to %0t. So like if in a particular state machine there is a case where the state machine has to be at rec, and at that rec the two signals have to be one of them have to be 1. So if that is not correct, then this assertion will be fired. So it's basically a checker way. It's basically a check to see whether your protocol or your design is behaving correctly or not. So concurrent assertions describe behavior that span over time, as I already told. And unlike immediate assertion, evaluation model is based on a clock, so that a concurrent assertion is stored only at the occurrence of a clock tick. So only at POSH clock or after some POSH clock, this assertion is fired. This concurrent assertion is fired. There are four different layers in a concurrent assertion. One is Boolean expression, then there is sequence expression, then there is property declaration, and there is verification directives. So Boolean logic does not have the concept of time. You just check whether two signals are correct or not. Just like in the previous example, you just have checked that whether request 1 is 1 or request 2 is 1. If either of them is 1, then assertion is okay with that. So temporal logic is a Boolean logic with time as one or more dimension. If that assertion in the previous case, if that is checked with some temporal assertion, like request 1 has to be 1, and after some 5 clock cycles request 2 have to be 0 again 1. So in such kind of expression are basically fall into temporal logic. Sequence allows us to define temporal nature of the sequence using temporal expression. So this kind of example is basically some temporal expressions in which request and after hash hash 2 and then there is a GNT. So this specifies that request shall be true on the current clock tick and GNT shall be true on the second subsequent clock tick. So this kind of expression is basically a sequence a layer, and it can, and through this it actually checks for that for the two clock edges, that the first clock edge and then the next and then the next. If this kind of behavior is not coherent, then this assertion will be fired. So by this you can actually write an assertion, and this is a very effective way to see whether your design is behaving correctly or not, or whether your design is actually showing some errors or warnings or notes or whatever it is possible. So these assertions are really helpful in our verification, and they are a very important source in case of negative testing as well, when where you want to see whether the DUT shows incorrect error, whether the DUT shows correct error according to specification if false values are fed into the DUT. Okay, so like this we have done all the basic modules of system Verilog. We are done with classes, we are done with testbench features of constraint randomization. We are done with interfaces. Then we have looked at the interprocess communications, and you will have a ALU example with you where the code is written, and you can actually simulate it on a test bench. This test bench is basically to give you a very basic feel of how a DUT is, how we started to check the DUT through our test bench, and this will actually give you a good understanding of how an ALU can be verified very easily. In this case, as you can see that there is a module test, there is an interface A1 which is done new, then there are two signals AB, and then there is a select operation. So since we have 4 operation, I have taken a 2-bit select operator signal, so 0 1 2 3 4. So then there is a result, DUT result, and there is a DUT result class. So result DUT is the output which the DUT gives, and result class is the expected result which should come out of addition, multiplication, subtraction, or division by the ALU class which we have done in slide